Okay, so we were talking about quotient space. So when you introduce some equivalence relation, so by introducing equivalence relation or equivalence classes, whatever you want to call it, equivalence classes, what we did is that we decomposed set X into mutually disjoint equivalence classes, and the set of all these classes, which are also in fact sets, is called a quotient space. And the set, let me put this in a bracket because you should remember that the equivalence classes, they are also sets. Okay, and the set of all classes which are sets is called a quotient space. This is the formal definition. And we denote the quotient space with X slash this equivalence relation. So this denotes the quotient space for some set X where some equivalence relation, the symbol equiv, is introduced. Okay, and the element, let's call that element A prime, that belongs to some equivalence class A, is called a representative of class. Okay, and now we will try to see some examples, and these are pretty interesting examples. But before I move into the examples, I would like to mention one thing, is that note that when you are talking about this equivalence relation, equivalence classes, you are doing some stuff with some sets, and since you don't specify anything about those sets, these are in general abstract. But if you consider your set X to be some space, and by space it's actually a topological space, but since we didn't define what is a topology, I'm not going to dive into that right now. Instead, for now, take the space of X is the your usual space-time, your usual three-dimensional space or four-dimensional space, and so on. If you do that, then you can do some interesting stuffs with some geometric figures. So this is a an assumption for now. For now, we treat X with our usual notion of space. Okay, and let's say this is your example 1. Let X and Y are some things that x and y both belongs to the real number line, and they have some sort of equivalence relation where y equals to x plus 2 pi n, where n belongs to z, integers. Okay, and this is true. You can show that under this sort of condition over here, x and y is indeed a equivalence relation. And first we gotta show that. So this is the proof. First we gotta show the reflective property, right? Reflective property. So take this relation. You write it as y equals to x plus 2 pi n, right? And n is n belongs to z. So you know from reflective property that reflective property tells you a is equivalent to a, right? And if you put n equals to 0, then you have y equals to x. But it doesn't tell you that y is equivalent to x. How do you do that? Well, you suppose that this x is equivalent to y, right? In the very beginning, that you have this equivalence relation only if you have this sort of a relation where x and y belongs to some real number and y is related to x with this relation. Then if this is the case, that means you are saying that, oh, it should be an equivalence thing, right? Then instead of y, what you can do, you just put x. So this is your reflective property. And there is another way. Some people, what they do is that they take n equals to 0, and since the difference between them is 0, they also call it they're equal. And when they're equal, they should be equal they should be equivalent to each other. But I personally don't like that approach, so that's why I prefer to this one. But you can do that as well. The second property is the symmetric property. Symmetry. If you don't remember, this is just if A is equivalent to B, then B is equivalent to A. Okay. So again, let's try to use the relation that we have at hand right now. This is x plus 2 pi n, right? And now what we say is that for all n belongs to z, x plus 2 pi n belongs to R, right? Because x already belongs to R, and for any n that is a integer, x plus 2 pi n is also in R. Similarly, you can show that this x equals to y minus 2 pi n. It's coming from this relation over here. And for all n belongs to z, you can say that y minus 2 pi n belongs to R, right? So both x and y, they belong to R, because y minus 2 pi n is just x and x plus 2 pi n is just y, right? Is this, do you understand, like, you understand this, right?
Yeah.
Okay. So from there you can write x is equal to y, and since again why you can write this x is equivalent to y, well, by definition x and y both of them belongs to R, right? That was the first thing. That was by definition or by the statement of the problem. And the second thing, you see that y and x are related with this, they're related by this equation. So let's say at first y belongs to R, okay? And after you imply this equation into your problem, where x is something that belongs to R, and then there is this 2 pi n thing where n is an integer, it also belongs to R. So what you are essentially proving is that even after using this equation, your y is in R, just like you started before. So that from there you can write this x is equivalent to y. And when you say that you start with some x belongs to R and y belongs to R, and you use this part, you can write y is equivalent to x. So that is your symmetric property. And the third one is pretty straightforward. It's called transitive. If you recall, if A is equivalent to B and B is equivalent to C, then that will imply that A is equivalent to C. So to prove the transitive property, we again start with this relation 2 pi n, and from here you can see that y minus x is just 2 pi n. What is 2 pi n? This is some number in the real line, right? Is that okay?
Yeah.
Okay. So this is what we do at the first line, but what I do right now is something like this. Let's say y minus z, where z is again something that belongs to R, is also related by this equation. And instead of m, let's call it instead of n, let's call it m, where m belongs to z as well, right? And you use these two equations, and you just subtract them or add them. Let's say this is 2, this is 1. What we do is 2 minus 1. If you do that, then you will have this y minus z minus y plus x is equals to what? 2 pi m minus n, right? So you can see that this 2 gets cancelled. X minus z is equals to 2 pi m minus n, and m and n, both of them belong to some integer, right? So m minus n also belongs to that integer. So this x minus z belongs to R. So within this type of mapping, since x minus z belongs to R, you can say that x is equivalent to z. So under this sort of mapping, you have this equivalence relation. Is that understood? Is there anyone who didn't understand stuff? It might seem a bit weird, okay, at first, but if you do some if you do some exercises, you should be fine. For example, I can give you an exercise. Let's say we have some AB. These are just two. For now, you can consider them as some numbers or coordinates. This AB is equivalent to some CD, okay, with the condition that A, B, C, D, they belong to this. I mean, yeah, all of them belong to the real numbers, but you should understand that this is not a problem on a real line. Rather, what I should really say is that A comma B belongs to R square. Similarly, C comma D belong to R square on the same space, okay? So what is the condition? The condition that, you know, a square plus b square is equals to c square plus d square. So how do you do it? Well, you have this condition, this guy over here. Now you try to prove what we did a little bit earlier by using this one, and you can show this. Try to do it. If you cannot do it, I'll solve it for you, maybe in the next class or in the next tutorial class. Just let me know. And the geometric figure for this guy, the geometric interpretation is something like this. These are the sets of all the circle, like this one. All the circles are equivalent to each other. So how do you interpret it? Well, these are just uh, giving you points that are that are of the same distance from the origin. For example, take this circle, right? And all the points on this circle has the same distance from the origin. Let's say this circle corresponds to this a square plus b square equation, okay? And let's say this circle over here corresponds to some c square plus d square. How are these two circles equivalent? Well, they're equivalent in a sense that all the points in on the top of their perimeter, they're of the same distance. By same distance, you know, they're of the same distance. That's what's given in this equation. It might not look like much, but that's kind of like the geometric interpretation for that. And the example that we did earlier is that y equals to x plus 2 pi n. It's a very nice thing. This is, let's say this is your real number line, and let's say this is x. So let's say this is x plus 2 pi. Let's say this is x plus 4 pi, right? When this is equals to that, so this will be x minus 2 pi, and so on. All these points are, you know, equivalent to each other. And when we say that these points are equivalent to each other, we mean that they represent the same point. They're essentially the same thing, okay? And that's why what people do is that people glue these points together. So if you just take this point, and if you glue it together, you get a circle. This is the only x. And all these points over here, they're the same thing as this point over here as well. And this type of procedure is often called identification. So if you have studied some special relativity, or general relativity, or any other stuff, this identification is similar to a periodic boundary condition, or a periodic condition. This example over here on the real line. Let's say we're moving in a straight line, and let's say some person is standing over here. Let's say he's person A, and you are the person B. You are going from point, let's say C, to point D, and let's say this is point E. You see this person on point E, you move from E to D, you see this person again, and so on. And you can make some interesting geometric figures by this type of identifications, and I can show you one. Let's say this is a square, okay? What we do is that we identify these two arms. Another color. We identify, or so to say, we define some equivalence relation. We are not going to discuss what that is, but for now, what we say is that we identify all the points over here to all the points over there, like this. So that's why I drew this arrow. You are identifying all the points on this arm with all the points on this arm. Excuse me. Sorry, there was a phone call. Yeah. So you identify these two arms as the following. All the points over here. Let's say this is the left arm and this is the right arm. You identify all the points of this left arm to all the points of the right arm, right? And since we regard the equivalent points to be, they represent the same thing, what we can do right now is that we can glue them together. And if you glue them together, this will be something that will come in the intermediate of this gluing process. And these arrows are important. This orientation is important, as you will see a little bit later. This is, you are bending the sheet or something without tearing it apart. And finally, what you have is a cylinder. And this is the line. Here, these two arms, they were glued together. Okay. This is a cylinder. What if you identify these two arms in the opposite direction? That's where the Mobius strip come in. Let me show you how. Let's say this and this. So that means you are identifying the point over A, let's say, with some point along this line over here, which is denoted by B. And similarly, let's say this is another point C. You are identifying this point with this D. Okay? Do you understand what I'm trying to do? If you don't understand,
could D be further along on the other side of B, since you would have to flip it? D should be below B, right?
D should be
because you would have to flip AC in order to match it with.
Yeah, the figure is not very accurate. Yeah, sorry about that. So this is like how you're identifying stuffs, right? Like it's like what I try to think, like take this figure for example, the cylinder one. Take this one and think of it as a mirror reflection. Okay, you can think of it. It's like a symmetric reflection, but here you have a reflection, but then you invert the reflection. That's how I think of it. Yeah, drawing is hard. Sorry. So it should be, yes, Saif is right. It should be below B. No, like fish. Okay, that drawing is not very accurate, but you understand what I'm trying to do. Like সবাই কি বুঝছে নাকি? না বুঝলে বলো।
লাইক একটা স্টিকের দুইটা পয়েন্ট যদি ধরে তাহলে এটা রিফ্লেকশনটা উল্টা আসবে ওরকম কিছু।
আমি যেভাবে চিন্তা করি
পা থেকে মাথা এরকম।
হ্যাঁ, লাইক আমি তোমার রিফ্লেকশন নিব। Like this is how it works from my point of view. সেটা হচ্ছে যে this is the mirror, right? Then this is you. First you know make a reflection of yourself, and then you flip it.
Yeah, okay. Yeah.
Like oh sorry. Yeah.
মাথাটা নিচে। Yeah.
And you'll see when we construct the Mobius strip, this is the exact thing that happens. So let me draw the square box again. This is our box. We identify these terms like this. So in the intermediate process, we will have something like this, right? But we cannot glue it right now because they're, of the opposite orientation. So the points wouldn't match up, so to say. So what you can do is that you can bring these two arms, closer. Okay. And then you flip one of the sides. Let's say this side. You flip one of them, and then you get the Mobius strip. You flip one of them, then their orientation is now, on the same direction. these arrows, let's say we are measuring directions with these arrows, they're on the same direction, and you finally get the Mobius strip. And the Mobius strip looks something like this. If it were a physical class, well, it would have been more easier to demonstrate this. So the Mobius strip, how to draw the Mobius strip, it's really hard. I cannot draw things like yeah, should be. So this is a very interesting object, and on a Mobius strip, I think everybody knows, everybody here knows this, that if you start from this surface, this inside one, and then you come out to the outside like this, if you are standing like this over this, let's say this is inside, okay, on the inside, then on the outside your orientation will get changed. So this is a Mobius strip. And there are plenty of more stuffs that you can do, funny stuff that you can do. I really cannot draw the Klein bottle, so I'll leave that up to you people to figure out like how you draw a Klein bottle in 2D. I cannot draw it.
I mean, Klein bottles have to exist in 4 dimensions, so it's even difficult to do in 3D.
Yeah, you have like you have to intersect the two heads of the cylinder, and for doing that you need another dimension. You cannot do it.
People use color for that, like color gradients. Yeah, 4-dimensional, yeah, double channels on that.
I don't know about the computer simulations regarding the Klein bottle, but there is something pretty easy, and I will show that. This one. Okay, so let me use different colors so that you don't get confused. Which one is getting identified with which one? You understand which arms are getting identified with which arms, right? These blue guys, they are getting identified with each other, and the white guys are getting identified with each other. So this is pretty easy. Again, in the intermediate process, you will have something like this. This line, and it will be a cylinder. That's understandable if you identify these two arms, right? And then we have to identify these blue arms as well, which has the same orientation. So instead of drawing it like this, I should have drawn it like this. That's easier to visualize. Now what you do, you just stretch it and glue these two blue arms together. If you do that, you get a donut, or so to say a torus, with a handle 1. And let's say this is the, I'm not very good at drawing, so this is where the gluing happened. The two faces of the cylinder, you take a pipe, you have super strength, so you bend it and you glue the faces together. So this is how you get a torus. And by genus 1, I mean there is, or a handle 1, I mean there is this hole, this guy. Okay. And even in Nakahara's book, I think I gave an animation video to you people that if you have an octagon, you can identify the arms in such a way that it becomes a 2 torus. By a 2 torus, I mean there are 2 handles. These are also called handles, these holes. And at this point, you might ask, okay, we are drawing this stuff geometrically. Yeah, what about, for example, take this octagon case, for example. It's not very easy to, intuitively understand how this octagon can be transformed into this torus. And this is this is coming from some equivalence relation, right? So this 2 torus will be a quotient space of this octagon. This 1 torus will be a quotient space of this figure over here. So how do you do it analytically? It has something to do with something called a cell decomposition. part of an algebraic topology. When we do homotopy, I think we'll discuss cell decomposition, where we can do some abstract math, some algebra that will lead us from, you know, these guys to these guys over there. But for today, this is the essential idea. And one thing, if you have noticed, that what we did was that, you know, we only stretched or shrinked stuff, you know, glued it together, but we never tore the, you know, surface or the figure that we are dealing with. So that's the essential idea of topology. And in fact, what you have noticed is that we didn't even care about the distances, right? So that's the thing about topology. Geometry cares about distance. Topology doesn't. Topology is something, you know, it's a more general study of spaces that you can have. So that is pretty much it for today. This is the part where I stop. Now, if you have any questions, you can ask.
আচ্ছা, ওই যে টোরাসের মানে যেই দুইটা পয়েন্টকে আমরা একসাথে করছি, ওইখানে একটা মানে রিং এর মতো থাকবে, যে মানে যেটা হচ্ছে,
Yeah, I mean, I drew that a bit earlier, but it looks nasty. Like, you're talking about this, right?
হ্যাঁ মানে এটা তো থাকতে হবে, রাইট? মানে এটা তো আই মিন সরানো যাবে না, ইন দ্য সেন্স যে এটা দ্বারা আমরা বুঝবো হচ্ছে যে ওই স্কোয়ারটার টপ আর বটম আর্মস গুলো হচ্ছে ওইখানে গিয়ে ম্যাপ হয়েছে, এরকম না বিষয়টা?
I mean, I don't know whether that's very important or not. I mean, for me, it's not. But yeah, you can leave those things. But will you be able to draw all the points? You know, let's say you identify this arm with this guy. Can you show these two gluing points over here? It's very tough.
না,
to
এটা
do that.
যাবে না।
It's very tough to do that. So, দরকার নাই তো। তুমি তো বুঝতেছো যে কোন দুইটা আগে আছে। Yeah, but তুমি রাখতে পারো চাইলে। চাইলে রাখতে পারো। আমরা তো রাখা কি করব না, উইল মোস্টলি ডিল উইথ টেকনিক্যাল প্রবলেমস। দিস ইজ এটা হচ্ছে জাস্ট একটা ইনটুইটিভ আইডিয়া যে এটা একটা কোশ্চেন স্পেস। ওকে, সো এনিওয়ান, এনিথিং এলস?
If you had the two white arrows that are pointing upward, if they were pointing downward, you would get another donut, but somehow with one of the edges pointing in the opposite direction, right?
What you're saying is something, is it something like this? Like this one, this one, this one, this one?
I meant like the two ones that are pointing up, rather they would be pointing down. Would that cause, like, you were drawing the circle in the donut, right? But they one would have the thing flowing
you are talking about the
clockwise, and the other one would have it pointing counterclockwise.
That's what, that's the movies. Sorry, that's the Klein bottle. Like, this one, because if you transform this to a cylinder, let's say this is like this, and this is in the opposite direction, right? And yeah, this is the Klein bottle.
I see.
So there is a nice animation, I think I saw it somewhere, but I don't exactly remember where. What they did is that, you know, এটাকে stretch করছে like this. Let's say this was the cylinder that we initially started working with. Then what they did, they stretched the bottom part like this. Okay, and let's say this is the arrow, so it should be on the opposite direction. This is going like this, so whoosh. Now you see that these two guys are you know, now they have the same orientation, right? After you do this kind of stretching. And then what they do is that take this, whatever this is, stretch it again, and they make a push, like they intersect. It intersects, and finally you have this guy, and this is your Klein bottle. Exactly. So I cannot draw the Klein bottle. Like, is it some, how to draw this? Like something like This maybe. I don't know how to draw it. I saw the figure on the book. I tried to draw it, but I couldn't. But this is the idea. Like, if you want to understand intuitively well, these two, they have this some sort of this opposite orientation. But you need to, like, you want to identify them, right? So you have to make them similar, and this is one way to do that. And this is the client bottle, yeah, and it's a non-orientable surface, by the way. If you read the book says that orientable surfaces where these surfaces are definite and stuff, and in non-orientable surfaces there is there is not a proper direction or something like that. But this orientability or non-orientability, this is something we will discuss when we talk about differential forms. That is something we will discuss after we talk about manifolds and all that. Okay.
I actually heard that if you cut a Klein-Bottle in two halves lengthways, then you get two Mobius strips that are opposite in orientation.
Two Mobius strips in.
Well, Mobius strips, like one is left-handed, the other is right-handed. They don't have an orientation.
Like, yeah, like this, but it has this whole Mobius orientability, right?
Yeah.
এটা কি অন্য ওয়েতে আইডেন্টিফাই করা যায়? আই থিঙ্ক করা যায়। সেটা হচ্ছে যে
I mean, I've seen this being done like in a physical demonstration.
Oh, yeah. Oh, okay. You just twist the Mobius strip once again, okay?
Yeah.
You get, yeah. And then you tear something, and then how this guy generates. Like, এটা আমিও দেখছিলাম, but ভুলে গেছি। And I think the way you can generate a two Mobius strip is something like this. যদি আমি square রাখি, I have to identify these two guys, in the opposite direction. That's fine. But then, instead of this, I'll do this. I think this should be something, I'm not exactly sure right now, but I think this is the double Mobius strip. Because first what I can do, I can try to glue these two guys together, the usual Mobius stuff, and then I can try to glue these two together from that Mobius strip I have. So I have to, I don't know how you'll do it, but it can be done, I think. But I need to check this, okay? The double Mobius strip should essentially result in this guy. Okay, I'll check about the double Mobius strip. It's a very interesting object. Okay, anyone, anything else? Okay, then I think we should stop the recording right now.